Morning, you 11s. Hey guys, good to see you all. Thanks for coming. Right, okay guys, so we're continuing with rates. This is Kinetics lesson 4. Okay, so I'm gonna get straight into it. Already done the register. Lessons all prepared. There you go, get rid of all that stuff. Right, and we're in. Morning, you 11s. Ah! Hey guys, good to see you all. Thanks for coming. The sound's not great today, is it? I wonder whether or not it's on a funny setting. I wonder if I can just fiddle with my, hang on, I'm just gonna have a quick look at my microphone. If I go for that one and then change it to that one again. Right, I'm hoping that's gonna be a little bit better on quality. Oh, maybe it's because the microphone's coming up, it's possible. There we go. Is that better, guys? Give me a quick shout on the chat. It sounds fine to me. Ah, thanks. Right, okay, guys, let's crack on. I like it. Okay, so today's title. Oh, I think I've lost my charger there. I'm going to put that back in. Okay, so today's title is rate graphs. This is lesson 4 of kinetics. So the first thing we need to do is we need to understand our rate graphs. We have to understand what the rate graph is doing, why it occurs, why we see the shape that we see, and explain why reactions slow down, and then calculate initial rate, tangent rates, and average rates. That is my task today. I'm actually also going to add in an extra learning objective. I want you guys to be able. I'm going to change my pen there. Change my pen to black and reduce the size, maybe small. I want you guys to be able to predict changes in graph. That's it, just predict changes in graph. Okay, so understand rate graphs. Okay, now, unfortunately, I've got to do this. This lesson's very different from what I would actually do in class. And I'm still tempted to try and give it a go. And it would be a very entertaining exercise to see if we can create a rate graph. Okay, so here's what we're gonna do. Oh, this is gonna be a real challenge, guys. Okay, I need as many people there as I can. Right, okay, fingers crossed. I'm actually going to do another thing as well. I'm gonna turn my, by the way, my laptop has crashed twice when I turned the camera off. Please don't crash, please don't crash, please don't crash. Oh, okay, it survived. Whew. Okay, guys, are you ready? I need your help here. Okay, right. So what we're going to do is there's 10 whites and 10 greens. I'm just going to restart. I want to yes, that's perfect. Okay, 10 whites and 10 greens. Okay, I need 10 people in the class. What we're going to do, I'm just going to quickly hang on. Before I do this, I'm going to show you what's going to happen. So when I press go on this reaction, watch what now happens. Yep, when the whites and greens collide, I'm going to turn up the temperature. Just turn it up a little bit. There we go. There we go. So when the whites and greens collide, they turn into whites and greens. That's terrible. When the diatomic whites and the diatomic greens collide with each other, they turn into a white and green. So what I'm going to do is I'm going to give 10 people in the class. Yeah, I volunteer as tribute. Amazing, Ashley. Why does it sound like a Hunger Games? Okay, I'm going to give 10 people in the class a molecule, and you have to watch it. So, for example, I don't know if you can see my pen. Right, there's 2 whites left. Those whites I may have given. So the white at the bottom I might have given to Shan, and Shan would have to watch it. And what she's going to do is, I need those 10 people in the class. I don't know what OFC stands, of course. Okay, so can those 10 people, so I'm going to name 10 people. Can I have, this is going to be a mess. Ashley, Shan, Ben, Toby, Nick, Ruby, Anna, Moses, Rue, and Tong. You 10 people, you need to get your mobile phones out and you need a stopwatch. Can everyone do that for me now? Once you've got your stopwatch up, can you give me a quick thumbs up on the chat? Or just say, got it. Yeah, so I've got all 10 people sitting there with their stop clocks ready. Okay, so I'm going to try and space the whites out as best I can. So it's easy for you guys to see. Oh, nah. Come on, that'll do. Perfect. Okay. Yep, I've got 2 people. Got it, Anna. Yep, Ben, got it. Well done. 4 people have got their stopwatches up. Got 5. Okay. Here's the next bit. This is going to be so cool. If this works, I'm going to be absolutely staggered. Right. Okay. Ruby, here's yours. That's Ruby's. Now, don't take your eyes off it. You need to make sure that you know and you've got it and you don't lose it. This is going to move around. You can't lose it. Yeah. I'm then going to give it. So Ruby, there's yours. Ashley, there's yours. Anna, there's yours. Then Ben, here's yours. Then Moses, there's yours. And then Rue, there's yours. And then Shan, there's yours. And then Nick, here's yours. Yeah, and then I can't remember who else I chose. Who else did I choose? Where's Toby? Yeah, I can give Toby one. Did I give Toby one? Did I? Toby, here's yours. One more person. Who haven't I given one yet to? Who haven't I given one to yet? I had 10 people. Who haven't I given one to? I can't remember. Someone help me, please. Quick. Come on, guys. Oh, who was it? I can't remember who it was. Tong, I haven't given you yours. And this one here is Tong's. Okay. Does everyone have their molecule? Oh, was it Vic? So I've got Ruby, Ashley, Anna, Ben, Moses, Rue, Shan, Nick, Tong, and Toby. Okay. You've all got your molecules. Right. When I press go, when I press normal, yeah, when I press this button over here, you guys are going to start your stopwatch. As soon as your molecule goes pop and turns into a white-green, stop your clock. Are you ready, year 11? Holy moly. Are you ready? 3, 2, 1, go. Three more to go. 4 more to go. Don't take your eyes off it. Don't take your eyes off your whites. 4 to go. Come on. There's another one. 3 to go. 3 to go. Not every collision results in a reaction. Done. 2 to go. 2 to go. Concentration of whites has dropped significantly, so the rate's slowing down. Come on. Come on. It's so close. Done. 1 to go. Oh, no. Come on. 1 to go. Come on. 1 more to go. Come on. 1 more to go. Up. Come on. Waiting for energy to be passed on in a collision. Oh, come on. Come on. No. Come on, one to go. One more to go. The problem is the concentration of white and greens now is incredibly low, which means it's taking ages for the reaction to happen. There's only one white per unit space now. Come on. That's it. Come on. Come on. Come on. Oh, that's so close. One to go. Come on. Come on. Come on. Come on. We've got to wait, guys. I'm sorry about this. We've got to wait. Gotta wait. Oh, the last one's taking so long. Oh, come on. Come on, green. Come on, I can see it. Nope. Come on. That white has slowed down so much. It's crazy. Come on. On opposite sides of the thing. Come on. I wonder how long it's been going for now. It's been going a while. Come on, green and white. Come on. Come on. Come on. Oh, got in the way. Come on, green and white. Come on. Come on. One more. I think that molecule just won't react. It will. Oh, it will. It's just the concentration's very low. Yeah, all the other particles are getting in the way. But we don't even talk about that, by the way. We just talk about concentration. Come on. It's heading up there. Come on. Come on. Come on. Come on. That's it. No, don't go that way. Oh, this is killing me. Metaphor of life. That's so funny. No, I'm not quitting. I'm not quitting. We're running it. I don't care. This is what chemistry is all about. Come on. Come on. Oh. Come on. Come on. Oh. I'm sorry. I can't. I've just got to leave it, guys. Just going to leave it. It's got to keep going. I can't. I'm just going to stay here and wait. I'm having a lovely lesson. Oh, it's so close. They keep passing. Look, they're so close. Come on. That green one's got lots of energy. Oh, come on. No, come on. Oh, no. Come on. Come on. I need a particle to hit that guy. Come on. Don't get in the way, you evil molecules. This is what happens. This is why it's so hard to tell when reactions have stopped. Come on, come on, come on, come on. Come on, somebody hit it. Push it in that way. Fight. Okay. Come on, they're gonna go. They're gonna do it eventually. Can't go on forever. Come on. This is gonna be the entire lesson. I'm totally okay with that, by the way, folks. Come on. Oh, they bumped into each other and it wasn't successful. Come on, come on, come on. No! This is killing me. Come on, this makes me want to cry. I know, right? This is what happens when you get to low concentrations. It's this boring. Did you know, by the way, when I was doing my degree, I had a practical that I had to watch for 3 days. And the first time I did it, I fell asleep and missed the change. I missed it. I had to then spend another 3 days. I had basically to put myself onto like these crazy sleep patterns, like sleeping at like micro sleep. It was an absolute nightmare. It was awful. Now what I do is I just set up my mobile phone to be able to record it. Oh man, how things have changed. Yes! No! No! Come on. That's it. Come on, somebody hit that white one. Hit it. Hit it. Come on. It's killing me. I can't believe this one particle is causing me this much trouble. Can we just redo the... No! I can't do it. I've got to do it. Come on. That's it. That's it. Oh, man. Okay. No, I want it. We're just gonna have to suffer in silence, folks. It's been going for like 4 minutes now. Come on. this little green, and then it's lost all its energy in a collision. Come on, come on. It's going to go eventually. Yes! Oh, it's done. Okay, can those 10 people now post their times on the chat, please? Post your things on the chat. Post your times on the chat, please, and I'm going to plot our graph. Holy moly. Okay, we can check back. Yeah, everyone lob on your times, please. 10 people should give me times. It doesn't matter. Just post them, guys. We can make this work. So time. What? Come on, guys. Post your numbers. I need your numbers. Toby, thank you. Moses, excellent. 1162. 47, I like it. Shan, 19. Yeah, I was recording. I caught Mr. Duncan's reaction. Oh, my goodness. Excellent. Look at this. Perfect. Right. This is where I now need to pause the chat because I now need to plot that graph. The last one was 7 minutes, 32 seconds. Okay, so I need to convert all of these to seconds. So Tongs was definitely the fastest by a mile. Check that out. Tongs, so this is going to be in seconds. Yeah, and we're going to start from 0. The longest one was 7 minutes 32. So 7.3, 7 minutes 32. So 7 times 60 gives me that, plus 32 seconds. Gives me 450 seconds. 52 seconds was the last one. And we're going to go to 10. So there's 10. There's 5. 1, 2, 3, 4. It's not perfect, is it? Attempt to try that again. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That'll do. Oh, no, didn't want to do that. So get rid of that. Let's go to 11. Why not? 10, 9, 8, 7, 6. I like it. Right, let's plot our graph. So the quickest time was Tong at 4.5 seconds. So what we now need to do is, let's make this easy for ourselves. Let's just make the last one 4 minutes, 450 seconds. Oh, let's make it even easier for ourselves. Let's make it 500. So in the middle is 250. And then what I can do is I can go up in 50s, can't I? So 1, 2, 3, 4, there we go. So 50, 100, 150, 200, 250, 300, 350, 400, 450, 500. There we go. I like it. Right, 450 is going to be the last one, 400, and then 350. Excellent. So Tongs, I'm going to plot this in red. Guys, I'd like you to plot the same graph, please, into your notes. So the first one happened at 5 seconds, which is there. Wow, that was really quick. The first one happened in 5 seconds. The next one, this is where I need to keep all my numbers. The next quickest one was Rue at 10 seconds. So the next quickest was Rue at 10 seconds. So 10 seconds was Rue. Then the next one after 10 seconds was Nick at 11:02. Then at 11:68 was Moses. Yeah, there we go. Then it all starts to slow down. Then our next one was 1962. 1962, so 20 seconds. Starting to slow down now. Yeah, after 1962 was Toby at 21:47. It's kind of the same. Right, so the reaction at the beginning was super fast. Now it starts, now we've got 40, so Ruby's there, she was the last one, 40 seconds, 47 seconds. Right, after that, they started getting longer. I'm missing people's times. I'm missing 4 people's times. Yeah. I can label these if you want me to, guys. Ben, the last one was 7. Ashley was 7. Anna, 1 minute. There we go. Anna, 1 minute 30. So that's 90 seconds. Anna was at 90 seconds, which is like there. Right, now at 90 seconds. Then who is there up at 2 minutes? I'm still missing loads of people's numbers. Where's everyone's numbers? Shan, what was your number? Shan, 20 seconds. I've lost loads of numbers. Who do I give people numbers to? I'm missing 3 numbers. I've got the last one. Ashley is at 7 minutes. That was over here at number 10 at 4:50. Yeah, I'm missing 2 numbers, guys. Who am I missing? Ben's 130. Nick's 112. 112, which is going to be about there, isn't it? For 9. There we go. And then missing another one. Doesn't really matter at this point. Mr. Duncan, I got 7 minutes. 7 minutes 12. Okay, cool. Okay. Anyway, I've kind of got my graph, guys. Because here's the graph. When a reaction takes place, it then slows down until it stops. So there's your very first rate graph. I've got enough data to be able to plot my graph. So it's really cool, this, because we get a very distinct shape in chemistry. Rate graphs are very distinctive. So now if we were monitoring, just to quickly mention, what we were monitoring here was the whites. This was the reactants. Sorry, no, hang on a minute. We were technically monitoring the products, weren't we? So actually, the white ones, I've just looked at that's the green and white line. The opposite would have done that, wouldn't it? It would have been the exact polar opposite if we'd looked at the whites. That's what you guys would have got. But it's nice to actually see that you get a very distinct graph shape. Yeah? Now, what we now need to do is we now need to look at each section of this graph. So at the beginning, so what we realize is, how can you recognize rate? It's to do with the gradient. So let's say this is experiment number 1. This is EXP number 1. Let's do another experiment. Should we do it again? Should we do it again? Oh, let's do it again. No, I'm not going to do it. I'm just going to, I don't want to do that again. It's not a good idea. So if we did this again, but I lowered the temperature, what's going to happen is that it's going to take even longer for this reaction to happen. And the gradient, the time taken for each point would drop. Yeah, it's going to go slower. Yeah, so what you get is the rate of the reaction. There's the first bit, by the way. There's the second one. So you can look at, so in terms of rate graphs, let's make some facts, right? I need to sort my head out. Facts. Number 1, but by the way, I've got loads of rate graphs over there. Facts. Number 1. The steeper, is that how you spell steeper? The bigger the gradient, I prefer steep though. The bigger, the higher the gradient, bigger the gradient, bigger the gradient, the higher the rate. Higher the rate. So for example, if I had a reaction, if I did 3 reactions and I got this graph, and I said to you, out of A, B, C, and D, which one was the fastest? Which one shouldn't say fast? Which one has the higher rate? On the chat, please. Yes, yes, purple, always sus. I'm so confused by what's going on in the chat. I have no idea. I'm so confused. Oh dear, Tiff's confused. Ink the time. Yeah, just don't worry about it. We're going to be watching for an hour. Intruders. Oh, Tiff's appeared. I've just joined to see. C. Thanks, Ben. Nailed it. Oh, Ipshita. It's so nice to see you. Ipshita's one of my subscribers from the UK. It's so nice to see you. I hope you're well, and I hope you're safe and well under the coronavirus situation. It's lovely to see you. Well done, everybody. The answer's C. So C is the highest, had the highest rate because it had the highest gradient. Yeah. And what I'm actually just doing here, guys, is I'm looking at what's called the initial rate. This green section, so this green section is called the initial rate. Fact number 2, the initial rate is the highest rate. I'm going to shrink my pen, it's way too thick. Is the highest rate in the reaction. Well, surprise, surprise, the start's the fastest. I think everyone kind of gets that. So, okay, just for fun on the chat. Hi, Mr. Duncan, all is well. Hope you were safe and well too. Oh, it's so nice to see you. Okay, just for fun on the chat, which one of my reactions, A, B, or C, had the lowest rate? Just for fun. So we've now got the initial rate, and we can compare these by just looking at the gradient and saying which one's going to be quicker. And it's really obvious in my eyes. Okay, so next. So another one's just happened. There we go. Look, they're still reacting at this temperature. It's just taking forever. B, thanks, Ben. Nailed it. Okay, so number 3. I'm changing my color all the way through here. Whoa, gone super skinny. Number 3. Okay, so if this part of, number 3, a chemical reaction, slows down as time progresses. We know this. And it became really obvious, didn't it? Progresses. Oh. So you spell progresses. Someone checked me on my thing. Thanks very much. Well done, Ben, Shan, Ibshita, Kieran, Tong, Wen, Ru. Thanks very much. B is the right answer. Reactions slow down as time progresses. Well, why? Why does the reaction slow down? So what we can now do is we can now draw another set of graphs. Yeah. So we can have, in fact, you know what? We don't need 3 of them. We don't need 3. Let's just do 1. So here's the green. Oh, I'm loving color coding. Here's the green initial part of the reaction. This is the initial rate. Initial rate, and it's the fastest. Also notice, by the way, that it's linear. Yeah, it's nice to know that. Right, now we enter into the next stage of the reaction. It's now starting to slow down. So the question is, why is this slowing down at this point? So question, why does a reaction slow down? Answer. Bullet point number 1. Yeah, this is a 3-mark question. Yeah. Particles, reactants, you can actually just say particles, but I prefer reactants. Reactants are being used up. Yeah, we saw this. Let's have a look. So I've still got a white on here. I've got 1 white left on this reaction and 1 green. Yeah, so the whites have all been used up. So is the greens. The particles are being used up. Now, that's not enough. Concentrate, less particles per unit space, concentration decrease, absolute less opportunities for reactants to collide. All of that, you've just given me the answer. Reactants are being used up. I'm going to reorder it. So the first one is Ben's answer. It's actually Ben and Kieran are actually the same answer. Yeah. Reactants are being used up. Therefore, the concentration of reactants drops. There are fewer particles per unit space. Concentration of reactants drops. Right, so that is the same as there are few particles per unit space. We're stating it in concentration. If you want to put the particles per unit space as well, you can do, but it's the same thing. Right, now there are going to therefore be fewer collisions. Collision frequency decrease. We're running into kick-ass now, guys. Collision frequency. God, and we watched it, didn't we? Oh, it was quite painful, to be fair. Collision frequency decreases. Therefore, fewer successful collisions. Fewer successful collisions. I'm so glad that my animation, this is what I do in lesson, by the way. I do this in class and I pick students, and we do this a good few times, but it's really nice that I managed to make this work. By the way, there's still a particle there. I'm just going to leave it running until I hear a pop. So the reaction is now slowing down. So section A, initial rate, highest rate. Section B, section red, slowing down. And then there is one final section. I'm just going to make that pen a bit thicker. section 3. And this is where the reaction has stopped. So stage number 3. So fact number 4, the reaction stops. So the question is, why does it stop? Has this stopped yet? No, it hasn't, because there's still a white in it. Yeah, it hasn't stopped, but it will. So why is it going to stop? So the section C is the reaction stops. Why? All reactants have been used up. Concentration drops to 0. I like it. Okay, that's amazing. So check my learning objectives. So understand rate graphs. Boom. Explain why reactions slow down. Boom. Loving this. Right. Calculating initial tangent and average rate. Okay, third learning objective. We're doing really, really well. Okay, at this point, I really need to start looking at real exam questions here. So now what I managed to find, a booklet with some rate graphs on it. I'll put this on the classroom for you guys to have a look at. It's actually quite nice. It didn't have enough of the things I wanted. Turn off. Right, there we go. And these are, by the way, these are from National 5. So these just happen to be rate graphs come from I think a US specification. What about the one is in excess? Oh, Isabel. Oh, I love the fact that you guys understand chemistry. You're absolutely right, Isabel. So you're right. So I can make somebody in excess, can't I? If I restart this, turn up the temperature. Let's go nuts. Let's go crazy. Excess greens. Yeah, go. Boom, super fast. Boom, 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 boom. Yeah, we're done. Oh, now we're done. No, now we're done. Lol. Temperature down, slow, stop, poof. Right. You're absolutely right, Isabel. So in this case, the reaction has stopped because because all of the whites have been used up. The greens are still in excess, and I'd want to actually state that. I don't think they'd actually care in an exam. Yeah, all reactants used up. If you really want to go that extra mile, and it's lovely, Isabel, that you've asked that question, because it tells me that you're thinking the chemistry through. That's so nice. Yeah. Why does the reaction stop? Reactant not in excess is all used up. There you go. In this case, they might even in an exam, I probably don't think at GCSE they'd expect you to be able, they could ask you to work it out. They could, but it would be really tough. That'd be really mean. Anyway, let's go back to some questions. Perfect. I'm going to steal you, graph. Yoink. New cut. Snip now. That's not what I wanted. Oh no. Oh no. Start again. Start again. Oh no. Try again. New. Hello. Gonna take you. Have you. Copy. In. Right. So can you put a new subtitle, folks? Calculating rate from graphs. How are we doing for time? Doing great. Rate from graphs. Love it. Okay. And le paste. That's French for paste, by the way, if you don't know. Yeah, of course it is. Yeah, definitely is. Right. Okay. Boom. Loving it. Okay. I'm loving it. Okay. So we can now identify the 3 parts of this graph. Oh, I've got people messaging me. Why are people messaging me? I don't know. They're not on the chat, so that's okay. If they're not on the YouTube chat, then I don't care. Okay, so we can identify the 3 sections of the graph. Number 1, let's use a ruler for this, by the way, because you guys have to remember to do this. I need a ruler. Where's my ruler? Ruler. Right, you pull out a ruler, and you set the ruler on 0. Set the ruler on 0. Now what you do is you rotate the ruler from 0 until you hit the line. There you go. And you can see where it leaves it. It's left it there. So there you go. So in fact, we can call it 10 seconds. Oh no. Oh no. It's just closed and crashed it. Damn. There we go. Let's find my ruler again. Draw ruler. Let's try that again. It's lucky that it saves as it goes. There we go. So I reckon it actually ends sooner than that. Yeah, it actually ends at about there. Oh, was it crashed again? No. Why is this not letting me? Uh-oh. Don't know what's going on. Okay, get rid of my ruler. No, I think it's going to leave it about there. Oh, I don't know what it's doing. Laptop's being lame. It definitely leaves earlier. It's leaving in about 8 seconds, I believe. Right, okay, get rid of my ruler because my ruler's causing me trouble. Right, so the linear portion of the graph ends there. Here's my initial rate. Yeah, there's initial. So you guys can, if you want to add this picture into your, I mean, obviously you can draw it into your notes if you wish. That's absolutely fine. Yeah, that'd be fab. But obviously you can also just like screenshot this and put it onto some digital notes if you want to. But this section here is the initial rate because it's the linear portion and it's the steepest. Yeah, so here's initial rate. So how do you calculate initial rate? How do you calculate it? Once you've found that linear portion, all you have to do, so we can go initial rate equals change in concentration of product. Right, my product is on the Y, and that's the volume of gas. That's perfect. So change in vol of gas in centimeters cubed. And then over change in time. And our time is in seconds. Love it. This is going to give us our units, you see. Right, now we can work out, we can actually input the numbers. The rate equals, what was my change in gas volume? 0 to 15. So 15 centimeters cubed of gas was made in 8 seconds. I like it. So my initial rate, 15 divided by 8, gives me 1.875 centimeters cubed per second. Isn't that lovely? Yeah? Mr. Duncan, can you get rid of the red line? Yes. There you go. There you go. But I'm just labeling that the initial bit ends at 15 seconds. Yeah. Right, now it's starting to slow down so that we can screenshot. Go back a few minutes ago. Yeah, just rewind the video. Yeah. I hope that makes sense for the initial rate. So you're just going for the linear part of the graph. Right, now what they're going to do is they're going to ask you to work out the rate at a point on the curve. Let's pick one. Let's pick here. It's just a nice point to pick. Right, they're going to ask you for the rate at 50 seconds. This is called rate on a curve, and this is tangent rate. I'm color coding everything. Tangent rate. Right, and I call it a tangent rate because you have to take a tangent. You guys know this. It comes from mathematics. So we're going to zoom in, and I'm going to get my ruler out, and I'm going to draw a tangent. Now, this is tricky because what you need, this is why you need a see-through ruler. Because when you do a tangent, that's a really bad tangent. You need to have, when you draw a tangent, there needs to be equal amounts of the ruler on either side of the graph. There you go. So that's a pretty good tangent. By the way, I'm marking where the ruler leaves the line, and it's about even, so I can now draw a tangent. There we go. Make my ruler vanish. Right, now that I've drawn a tangent, I can now use the tangent in order to calculate the rate on the curve. Yeah? So what I'm now going to do is I now need to get a delta y and a delta x from my tangent. So all I'm going to do is just pick easy spots. The bigger the tangent I use, by the way, the more accurate my result is. So I'm going to go from here. So 40 centimeters cubed. Then let's go to something nice and easy. Let's go to 70 centimeters cubed of gas. I think that's very reasonable. So what I've done is I've picked a delta y here, guys. I've picked a delta y. That's easy. I'm going from 40 on the line to 70 on the line. So I can clearly see that that's going to be a delta y. Now remember, gradient is delta y over delta x. Yeah. I'm not going to remind you of how I teach that. Oh, no, I won't do it. So we've got delta y, gradient is delta y over delta x, the change in volume, delta x, there we go. So our delta y is the volume of gas, which is 30, because that's going to be, the delta y is 70 minus 40. It's the change, remember. 70 minus 40, which is 30. So 30 centimeters cubed of gas. What I now need to do is work out my delta x. So to get my delta x, I'm going to change my color to make it slightly easier to see. This is where my ruler would come in really handy. Let's get my ruler out. I'm also going to make my my pen a bit easier to see. Right. So what I actually need to do now is I just need to pull out the time. There we go. Let's get my ruler out. That's dead in the middle of that square there. Right. So if that's 10 to 20, this is 10 down here and 20 down here. I don't know if you can see my pen or not. Yeah. How much more advanced are these concepts at AS? I'm 2 months into AS and I've seen a lot of changes from GCSE already. So just wondering. Well, Ipshita, I'm teaching this almost to an A-level standard, almost. So not a huge amount. It's more about the changes in rate graphs that happen. So actually not far from what I'm actually doing now. I'll show you the changes and I'll show you the comparative ones in a second. Okay, so anyway, 10, so hang on, each square is 2, 4, 6, 8, 10. So that's in between. So that's 7. So that's 17. So that there down there. So if I come down here, that's 17. And then what's the next one? The next point I picked was there. Use my ruler. Again, in between the line. Oh, no, actually, I could probably go on it, I reckon. No, it's a bit, yeah, I'm going to go on it. Why not? Make it easy for myself. There we go. So that's going to be 78. 17 to 78. That's 17 to 78. Oh, yeah. 78. 78 minus 17. What's that on the calculator? 78 minus 17 gives 61. So my delta x in time is 61 seconds. Now, if I get this right, the overall rate should be lower than the initial because it's slowing down. So 30 divided by 61, and I get a rate of, I'm going to get rid of all these numbers now. Yeah, and this is seconds. So that's, I now have a rate of 0.492, 3 sig fig. Yeah, centimeters cubed per second. Ipshita, just to quickly mention, just to say that the only thing you can't do, Ipshita, I hope you've been watching all of my AS videos, especially on atomic structure. The only thing you're not allowed to do at A level is you're not allowed to use the slash anymore. You have to use per time as s to the minus 1. Just a reminder. And anyone knows who's interested in class, that's what happens at A level. But GCSE, you're still allowed to do that. Okay, so the rate's slowing down. That's cool. So we've now worked out rate of a tangent. Yeah, not complicated, but it's tricky. It's easy to lose marks. They do give you a little bit of leeway on it, but it's not an easy process. Yeah, and they do like to ask these. These are grade A. These are grade A at GCSE. Yeah, it's also, by the way, a grade C at A level. They do ask these. In fact, they're more common at AS than they are at GCSE. They tend to ask you to do the average rate at GCSE. So let's now do the average rate. Right, so the average rate, I'm going to change my color for this. This is my last part of the lesson, the average rate. So the average rate is simply looking at the total changes of both things. So what's the total volume of gas I made? The total volume of gas I made was 65. So average is total change in product. In this case, change in concentration of product. In this case, 65 centimeters cubed of gas. And then over the total time, total change in time until stopped. Yeah, until it stopped. Now that's important because otherwise people could just use an infinite amount of time. But what you have to do is realize that it stops there, stopped at 90. Yeah, stopped at 90. Total change in time until reaction stops. Until reaction stops. So 65 over 90. 65 divided by 90 gives me an average rate, an average rate, AVG rate of 0.722 centimeters cubed per second. And we're done. I don't like the fact I can't read that, 722. Right, guys, that brings me to the end of my lesson. Absolutely spot on in terms of time. I'm absolutely made up with that. Oh, but I didn't do my extension. Oh, predict changes in graphs. Next lesson, guys. These are the predicting the changes in graphs. Yeah, and we'll look at that next time, guys. We'll do graphs part 2 for rates. Guys, I hope that was all okay. I'm going to end the lesson at this point. I'm going to turn my camera back on if I can. I'm being blipped on my phone or on my laptop. It's driving me absolutely crackers. Let's turn my camera back on. Enable. Oh, no. No. Enable. Come on. Enable device. Don't crash. Don't crash. We're back. Okay. I'll go back to StreamYard. Close my video. Start camera. Bring it back to this one. There we go. Hey, guys. Anyway, guys, it's been great to see you all. Thank you so much for coming. I hope it all made sense. Rate graphs they're tough and they require a good bit of practice. I'll post the questions that I found online onto the classroom for you guys to have a go over the half-term holiday. Ipshita, it has been so lovely to see you. I hope you're well. Have a great rest of your holiday. And if you need any support with the AS chemistry, please feel free to ask. I'll always do a webinar for you if you need it. Take care, guys. Have a great rest of your day and a great